Well, good morning, everybody here in New Mexico, and good afternoon to everybody that is east of the Mississippi, and then good evening to those that are over across the pond in Europe. Thank you, everyone, for joining us today. This is our final Planetary Sample Science Seminar series of the semester, and so we want to thank everybody who's been here throughout the semester for joining us along. And so we have our final talk. Before we begin, though, I do have a quick announcement. We do ask for those that have joined to make sure that your mics are muted. We will have a question session at the end. Throughout the talk, if you want, you can put questions in the chat as well, and we will get to that in the end. But we do ask that you please have your mics muted throughout the talk. Okay, so with that being said, I want to welcome Dr. Ananya Mallik today. So she is an assistant professor in the Department of Geosciences at the University of Arizona. She is an experimental petrologist who primarily uses high pressure temperature experiments to simulate processes on planetary differentiation and combines that with sample analyses and thermodynamic modeling to address outstanding research questions. She not only investigates differentiation processes on Earth, such as mass transfer mechanisms in subduction zones and deep volatile cycling, but is also an expert of lunar differentiation processes, such as investigating how hot and wet the moon is, understanding the chemistry of the moon's mantle, and the lunar crust formation processes, which is what her talk is today. And so with that, Ananya, please go ahead and take it away.
Thank you, Quentin, for the introduction. Okay, well, thank you so much for coming to this last talk in the seminar series. So today I will be talking about secondary crust formation on the moon and shed some light onto what we can understand about lunar differentiation from that. So as Quentin said, I'm Ananya Mallik. I'm an assistant professor in the Department of Geosciences at University of Arizona. And before I begin my talk, I wanted to acknowledge all my collaborators here. So big shout out to Isaiah Spring, who's one of the PhD students in my group. And actually, I will be showing some of the work that he's been doing in the second half of my talk today. Also, Arkadeep Roy, who's the other PhD student in my group, who's working on lunar processes. Pranavendu Moitra and Jason Kirk, who are my colleagues in geosciences, Rick Herwig at Arizona State, Lars Borg and Thomas at Lawrence Livermore, and then, of course, Chip, who you all know. Oops. Okay, let's see. Why is it not advancing? There you go. All right, so I guess I may be preaching to the choir here, but I still thought that just to make sure that all of us are on the same page, I will discuss a little bit about why crust formation or studying crust formation is important for any planetary geoscientist. So this is the Earth, but it could be any other planet, differentiated planet. And what we know is that the crust is, this outer shell of that planet is really important because it gives us insight into heat loss from the interior. The crust happens to be one of those layers that takes in a lot of radioactive elements, and so it determines heat production. Very importantly, it's the solid reservoir that's in contact with surface reservoirs, which means that studying the crust is actually key to surface interior interactions, which means that for certain planetary bodies, it can give us insights into the habitability. And very important for planetary exploration is that the crust is the most accessible solid reservoir. And so really studying the crust is one of the key to understanding interior processes. And this is something that, of course, has motivated the research that I'll be presenting today. And again, just going through the different kinds of crust and the different generations of crust and why the moon is really interesting when it comes to studying the crust. Well, we have the primary crust, of course, which is what we think formed by large-scale melting, by accretion, or due to some sort of heavy impact bombardment early on in the history of a planetary body. And on the Earth, this primary crust is likely missing. But on the moon, maybe thanks to the absence of some efficient recycling process such as plate tectonics, we do have the anorthostatic flotation crust, which formed from magma ocean crystallization, which we think represents the primary crust of the moon. And then, of course, if you go into the secondary crust, which is what we call crust that forms from partial melting of the mantle of a planetary body. On the Earth, we have mid-ocean ridges. And on the moon, we have different lithologies, crustal lithologies such as Mg suite, alkali and felsic suite, the magmatism that gave rise to that, as well as Mare volcanism. And actually, today's talk will be more focused on some of these secondary crustal lithologies. And then, of course, the tertiary crust, which forms by reworking of the primary and secondary crust. On the Earth, we have continental crust formation in arcs as an example of that. On the moon, maybe there are some later volcanism which reworked primary and secondary crust, or maybe some impact melt which formed later, which may have reworked primary or secondary crust. But no matter what, I think we can all agree that the moon is an excellent study location for studying the different generations of crust, especially the primary and secondary crust, and also that would shed light into lunar differentiation. And so this is a figure from one of Chip's papers that came out in 2015, where we see the mole percentage of anorthite and plagioclase on the x-axis and the Mg number in the different mafic minerals on y-axis. And then these different fields show the different kinds of crustal lithologies, of which this dark gray one is what consists of the ferronanorthosites, which we think are the primary crust. Then we have these light gray ones, which are sort of at the high anorthite content in plagioclase, as well as high Mg number in mafic minerals. And these form the secondary crustal lithologies, especially the Mg suites that are plotted here. And then there are these groups of rocks, which are alkali or felsic suite rocks, which are sort of probably the least understood of all these kinds of rocks. And in today's talk, I'll actually show some sort of a connection that we can build between these alkali or felsic suite rocks with the Mg suite rocks. Okay, so if we look at the ages of these different crustal lithologies, so this figure here is actually modified from this paper by Borg and Carlson that came out in 2023. So on the x-axis, we have age. So as we go to the left, it gets older. Or I'm sorry, as we go to the right, it gets older. And then on the y-axis, we basically have frequency of these different, these orange detrital zircons here. So what we see is that these orange fields that you see that represent the lunar detrital zircons, they have a peak, a very distinct peak at about 4.34 billion years. And then all these other lithologies, so these blue circles here are Mg suite rocks, which we think represent the secondary crust. And then there's this one pink square, which is a quartz monzodiorite class that was recently dated. And then we have all these other green lithologies that we think are things that crystallized, from the magma ocean. And then this square with the black circle is what we think represents the ferronanorthositic crust. So what we see is that the ferronanorthositic crust is about 25 million years older than some of the secondary crustal lithologies in blue and pink. Well, the pink one we don't know as yet, but I'll talk about that. But at least the Mg suite rocks and the ferronanorthosite, they have about a 25 million year gap between them, with the ferronanorthosites being older. And this goes well with the way we think the petrology of these lithologies are. So for example, if the ferronanorthosites are primary crust that crystallized from the lunar magma ocean, then obviously the secondary crust, which may have formed as a result of overturn, where these high dense cumulates that formed at the very end of the magma ocean crystallization, because they were so dense, they foundered and they sank, and consequently resulting in upwelling of hotter mantle from below, which may have resulted in partial melting. So the fact that the ferronanorthositic crust is expected to be older than this episode of upper mantle partial melting and resulting secondary crust formation actually bodes pretty well with this 25 million year gap that we see in the geochronology record. And also, very importantly, what we see is that these Mg suites, that QMD class, and this peak in detrital zircons, they all kind of line up at around 4.34 billion years ago, which is a very interesting observation just from this figure, as you can see. The other observation is from this figure here, where we have 147 samarium over 144 neodymium on the x-axis and 143 neodymium over 144 neodymium on the y-axis. And these different data points here are for Mg suite and that QMD class that were dated. What we see is that all of these lie on an isochron, which tells us that these rocks were derived from a source with similar samarium to neodymium initial ratio. So the fact that the Mg suite, the QMD class line up with the zircon peak at about 4.34 billion years, and the fact that the Mg suite and the QMD, they seem to line up on an isochron as well, which tells us that they were derived from geochemically similar sources, leads to this hypothesis that maybe the Mg suite and the QMDs, they're actually petrogenetically related. And if the hypothesis is valid, then the implication for that would be that there was a strong pulse of magmatism at about 4.34 billion years, which must have resulted in substantial differentiation and must have led to secondary crust formation. And the strong pulse of magmatism could be due to one or a combination of several factors, such as mantle overturn, where this dense cumulate layer may have sunk, resulting in rise of hotter upper mantle, and that upper mantle would have partially melted. There could also have been an episode of tidal heating at about 4.34 billion years, which was recently proposed by Francis Nemo and others, where they said that due to high orbital eccentricity at that time, this could have led to strong tidal heating and as a result could have caused substantial partial melting on the moon. And then, of course, there's also the possibility of an impact melting, especially an impact the size of SPA, where that could have also led to substantial magmatism. But no matter what the source of magmatism is, in this study, what we investigate is that if we have a partial melt from the upper mantle, whether that partial melt crystallization can actually connect the Mg suite and the QMD, and in turn, if that's a petrogenetic process that we can use to explain secondary crustal magmatism. And this cartoon to the right kind of shows what this process that we're trying to envision here, where we have these ultramafic cumulates which partially melt, and those partial melts could actually form these Mg suite along the cumulate line of descent, and the evolved liquid along the line of descent that may give rise to some of these evolved lithologies, such as the QMDs. And there may be some interaction with the primary crust as well. And in these models, we'll actually assess the extent to which this interaction with primary crust is required to explain these different crustal lithologies. So what we have done in this study is basically run models of fractional crystallization. So we have taken a primary melt composition that was reported by John Longy in his paper in 2010. And this partial melt composition is basically the partial melt of a mixture of olivine and some pyroxenes with a little bit of creep added into it. Then we use the thermodynamic code rhyolite melts. This code rhyolite melts has been used pretty extensively by scientists to investigate magmatic differentiation on Earth, but also for lunar magma differentiation as well, especially looking at lunar magma differentiation from primary to evolved compositions. We varied the pressure from about 0.05 to 0.5 GPa to see if what the effect of pressure would be on this kind of differentiation process. And then we also varied the FO2 from about IW to 1 log unit more oxidized and 1 log unit more reduced compared to the IW buffer. And then, of course, previous studies have suggested that some primary crust assimilation may be required for the Mg suite. And so what we wanted to do here was actually assess the effect of primary crustal assimilation on the cumulate and the liquid line of descent. And so we varied the amount of primary crust from 5% to 50%, so sort of two different end members. Okay, so this figure here, there's a lot going on, but I'll walk you through it. So these are the results from those, the modeling of fractional crystallization. So these are cumulate lines of descent, which means how does the cumulates that crystallize from their primary liquid, how do the cumulate compositions change as that liquid evolves, as you're fractionally crystallizing. So to the left, there are these four figures which represent the higher pressure end member at 0.5 GPa. And to the right, there are these four figures that represent the lower pressure end member at 0.05 GPa. And if you look at each of these figures, these are basically oxide-oxide diagrams. So these are MgO, magnesium oxide versus aluminum oxide, silicon dioxide, iron oxide, as well as calcium oxide. All these different colored symbols represent the different Mg suite rocks that we know of. And this tiny black or dark blue circle is the first cumulate that would crystallize. So, the starting point basically of these models. And then we also have these blue squares, which are the QMD compositions, just for reference here. So what you can see is that you start with the first cumulate, so this circle, and then you have these zigzag lines where basically these zigzag lines represent the appearance or disappearance of a certain mineral along the cumulate line of descent. So just as an example here, so we start with chromium-rich spinels coming in. So at some point, it's just chrome-rich spinel, and then magnesium-rich olivine comes in. And then at some point on the line of descent, plagioclase and orthopyroxene comes in. And then at some point, orthopyroxene goes out and clinopyroxene comes in, and so on. So this is the reason why we have all these zigzag lines here. And these arrows kind of tell you the direction along which the cumulates are evolving as you fractionally crystallize that primary liquid. The other thing to note is that some of these figures have black lines, whereas some of them have some red curves as well as blue curves too. So the red and the blue and the black curves, they represent individual FO2 conditions. And in most figures, we only see the black ones because the effect of FO2 is so minimal in these simulations that all of these curves mostly overlap with each other. So what we can at least infer is that FO2 does not have a strong effect on any of these lines of descent. So overall, what we see is that amongst the 0.5 and the 0.05 GPa, the cumulate lines of descent broadly match the scatter in the Mg suite lithologies that we have. And one thing to note here is that orthopyroxene comes on the liquidus only at pressures greater than equal to 0.3 GPa. So any orthopyroxene bearing lithology likely would have formed at pressures at least at 0.3 GPa or higher. This next figure, these next set of figures show the same cumulate lines of descent, but upon reaction with the primary crust. So to the left, we have the panel where it shows the lower end member of assimilation with just 5% of ferroanorthocytic crust. And to the right, we have a panel where we have 50% ferroanorthocytic crust assimilating. And as you can see overall that the 50% ferroanorthocytic crust actually makes the match between these cumulate lines of descent and the existing secondary crustal lithologies even poorer, whereas the match is tolerable for the 5% crustal assimilation, which tells us that the amount of ferroanorthocytic crustal assimilation that may have taken place during Mg suite petrogenesis was actually very little. The next set of figures here, these show how the liquid composition evolves as we fractionally crystallize a primary liquid represented by this blue circle here. And then as you follow the arrow, that's how the liquid evolves as you fractionally crystallize. So again, these are oxide-oxide plots here with MgO versus aluminum oxide, silicon dioxide, iron oxide, and calcium oxide. The panel to the left, again, is the higher pressure end member, whereas the panel to the right is the lower pressure end member at 0.05 GPa. And then these blue squares represent the quartz monazite compositions that we have available. And so what we see overall is that, again, if we look at the liquid line of descent and we try to see what best reproduces or matches with the QMD data here, perhaps the lower pressure gives a much better fit than the higher pressure end in this case. And then again, we looked at the effect of assimilation of ferroanorthocytic crust. So to the left, we have 5% ferroanorthocytic crust assimilation, and to the right, we have to the left, we have 5%, and to the right, we have 50% ferroanorthocytic assimilation. And if you look at these curves compared to the QMD compositions, what we observe is that there isn't much of a difference between 5 or 50%. So what we can say about the QMD is that the QMD is better matched by the liquid line of descent at lower pressures, but we cannot really put a limit on the extent of ferroanorthocytic crustal assimilation that would be required to produce them, at least in terms of major elements. So to sum up this part of the talk, so again, to go back to the original motivation that led us to the hypothesis, which is the fact that all these Mg suite lithologies, this QMD class and this detrital zircon peak, they all line up at very close to 4.34 billion years. And the fact that the Mg suite and the QMD, they also lie on the same isochron, which tells us that they were derived from geochemically similar sources. This led us to this hypothesis that the QMDs and the Mg suites are petrogenetically related. And so we investigated this process where we have a partial melt from the upper mantle that crystallizes, and as it fractionally crystallizes, the cumulates form the Mg suite, and then we find that the evolved liquids actually form the QMDs. So the key takeaways from this part of the talk are that the quad-sponsor diorites likely fractionated from melts along the differentiation of an Mg suite parental liquid, which suggests a common petrogenesis for the Mg suites and the QMDs. And the fact that there's the zircon peak at 4.34 billion years, that zircon peak may represent enhanced magmatism due to either overturn or tidal heating or perhaps impact, and that magmatism must have led to secondary crust formation. So this leads me to the second part of my talk, which is basically the work that one of the grad students in my group, Isaiah Spring, he is leading this effort. And so what he is trying to do is basically use trace elements to understand the petrogenesis of Mg suites even better, and basically focusing on one of the Mg suite samples. And I'll talk more about that now. So the goals of the study that Isaiah is leading are to use trace elements to infer petrogenesis of Mg suite sample. And the other motivation that we had was to extract the maximum amount of science that we can from the minimum amount of sample. And this is, of course, very important for planetary sample return missions. And we're not the first people to think about this. This has been suggested by previous authors as well. But we wanted to demonstrate this, the ability to extract as much science as we can from as less sample as we can, and see how far we can go. So what Isaiah has done is he has focused on this particular troctolite sample, which many of you here are very familiar with. It's 76535. It's a troctolite, which means it's basically mostly plagioclase with some olivine and then some minor amounts of orthopyroxene present. This sample is really special because it has very minimal shock effects, and it's the most pristine actually of the Mg suite samples, which makes it really special. And then if you look at the chemistry of the sample overall, so this is again a figure which shows the anorthite content in plagioclase versus the enstatite content of the Mg number in the pyroxenes. This red field here is where we expect the ferroanorthocytic crust to be, and this blue field here is where we expect the Mg suite to be. And so this square right here is where this particular sample lies. And so these are actually the 4 grains that Isaiah analyzed, and he did a suite of analyses on them. So what he did was he took these plagioclase grain separates and he mounted them in indium. And then he did tracks, edge-to-edge tracks, using both microprobe for major elements, as well as SIMS for certain trace elements. And then he did these laser ablation ICP-MS work where he basically measured these trace elements along these troughs that are marked by these green lines. So Isaiah has measured over 80 trace elements, over 80 elements in total, which includes trace elements as well. But for this particular study, we are only focusing on the rare earth elements because that's what we use to infer the petrogenesis here. But I do want to say that this is a manuscript under revision. And so hopefully once this manuscript is published, all of these 80 elements that we measured would be available to the community for any future study. And again, as we said, that we wanted to maximize the scientific findings from the minimum amount of sample, which, as we all appreciate, is very important for current and future planetary missions. So these are some results from SIMS analyses that Isaiah did. So basically, these are 3 different grains here, the top one, the middle one, and the bottom one. And then they show edge-to-edge transects over here. And then each of these colored symbols represent a certain trace element that was measured by SIMS. So qualitatively, what we can see right now is that these grains are pretty homogeneous. And actually, Isaiah came up with a metric to quantify the homogeneity in these grains, which I'm not going to talk over here. But hopefully, once his manuscript is published, you can take a look. And so you can see that these grains are actually very homogeneous, so much homogeneous that I don't know if Rick Hervig is on this call, but he commented that it was probably a waste of time and pretty boring. But the fact that these grains ended up being so homogeneous gives us confidence that these laser ablation ICP-MS that we did using those troughs actually gave us a robust analysis of the composition of the grains and the bulk composition of these grains. And I'll also mention one other thing here is that if you look at these 3 different grains here and we compare them, actually all of these grains are very similar to each other. So these grains are not only homogeneous within the grain itself, so it's not just intra-grain homogeneity, but also inter-grain homogeneity, which is very high here. And so this figure here actually shows the trace element, especially the rare earths that Isaiah got from these grains. And he also compared them with 2 other studies which had previously measured, these rare earths on plagioclase, but these were more bulk measurements. The fact that Isaiah's measurements agree well with the previous bulk measurements is a good sign, of course. And now we are going to use this rare earth element composition to actually infer what the parental liquid would be for this particular empty suite sample. Now, when it comes to inferring the parental liquid from what was measured in these individual plagioclase grains, there are 2 ways to do that. One is a simple inversion method where we take the composition, the measured composition in the plagioclase grains, and then we use a published partition coefficient from the literature to basically calculate what the liquid composition would be, but that liquid composition would be the liquid that was coexisting with the plagioclase, but that may not be the original unfractionated parental liquid. But in order to go back to what the unfractionated parental liquid may be, we use this forward model where what Isaiah did was he took a primary melt composition, such as the one that was proposed by John Longy, and he ran it through rhyolite melts to basically get the phase proportions that one would expect as that primary liquid crystallizes. And so this figure here to the right shows temperature versus percentage of fractionated mineral along the line of descent from the primary liquid. And so what you can see is that you have olivine crystallizing, and then at some point plagioclase comes in, and then there is a window here, a temperature window, where both plagioclase and olivine crystallize in proportions that are relatively close to what we observe in this particular troctolite sample. So what Isaiah has done is he has basically varied the amount of trace elements in this unfractionated primary liquid. And then he has used partition coefficients from the literature to model how these trace elements would fractionate along the liquid line of descent. And what he has done is he has done an iterative process where he varied the initial amount of trace elements in that unfractionated liquid to see that what is that amount of trace elements in the unfractionated liquid that would best explain the measured amount of trace elements in these plagioclase grain separates. And so this figure here actually shows the parental liquid compositions that Isaiah got from this study. So again, these are rare earth element figure. This is a rare earth element figure where you have these rare earth elements on the x-axis and the parental liquid composition normalized to chondrite on the y-axis. These blue diamonds here are the results from the forward modeling, which shows basically the unfractionated parental liquid. The orange symbols here, they represent basically the measured trace element concentrations in these plagioclase from the troctolite sample that was measured by Isaiah, but he did a simple inversion. So basically this gives us the composition of the liquid that was coexisting with the plagioclase itself, but that's already fractionated. And then these other solid lines show the parental liquid or the liquid that was coexisting with the plagioclase that was calculated by Isaiah using data that was published by previous studies. And then for reference, all these dashed lines in the background, these are different earth creep compositions. And so what we can see is that the parental liquid that we obtain, whether it's the unfractionated one or the more fractionated ones which coexist with the plagioclase, they're all very enriched in rare earths and are actually very close to some of these model earth creep rare earth element compositions. And so what Isaiah did was he did these mixing exercises between the primary liquid, which is that unfractionated parental liquid in these blue diamonds here, as well as the different model creep compositions. So what he did was he assumed that we start with liquid, this green glass here, which represents, let's say, a rare earth element poor liquid that's derived from the upper mantle. So a partial melt of the upper mantle. And then what he wanted to do was to see that how much of earth creep we need to add in to this in order to explain the parental liquid that he is getting for 76535. So this earth creep composition here is actually from this recent study by Haupt et al. And what he finds is that we need 50% of the model earth creep to be assimilated with this green glass in order to explain this parental liquid that Isaiah obtained. Again, this is another model earth creep composition and the same mixing exercise. And here Isaiah finds that about 30% of earth creep is required. And then this last one is, again, another model composition of earth creep. And again, here Isaiah finds that about 30% of earth creep is required to be assimilated with primary liquid from the upper mantle in order to explain the parental liquid that would crystallize troctyl 76535. So the petrogenetic model that Isaiah came up with based on this particular study is that we have partial melts from the early LMO cumulates, that's the upper mantle here. This partial melt assimilated earth creep, and then it basically crystallized, and along its cumulate line of descent, we formed all these different Mg suite lithologies, such as dunites, the troctolites that he has studied, norites, etc. Now, one thing to keep in mind is that, of course, the sample that we studied is an Apollo sample, so it's from the near side, but Mg suites, at least from remote sensing and spectroscopy, we know that they're global in occurrence. So this figure to the left from Tap Crystal's paper in 2023 shows these pink circles, which are candidate Mg suite exposures globally on the moon. And then this one from Kian et al. 2024 actually shows the SPA basin right here, where all these colored circles are different exposures for Mg suite. So the Mg suites are global, but creep enrichment in these Mg suites are not global. So the Apollo Mg suites are creep rich, as we just found from Isaiah's study, but there have been reports of Mg suite samples from Chang'e 5, Chang'e 6, so both near side and far side, as well as meteorites that are actually creep poor. So based on this, what we can say is that creep cannot be a requirement for Mg suite formation. And in fact, the 30 to 50% earth creep assimilation that Isaiah finds, if indeed that much of earth creep was assimilated, that would have major penalty in terms of major element chemistry. And I say this because if you look at the magma ocean crystallization models, then that very last bit that should have given rise to earth creep was actually very, very iron rich. And so 30 to 50% of assimilation of that iron rich liquid would have severe penalty on the mg number of the liquid overall. And this is why we are following up on this work that Isaiah just did, which is we are verifying this petrogenetic process by not just, well, he already analyzed the plagioclase from that sample, but we are also going to analyze olivine and orthopyroxene to see if that same story holds up. And of course, as I said, that there will be a severe penalty on the major element chemistry if there was so much earth creep assimilation. And so what Isaiah is doing right now, he's running some phase equilibria experiments to actually see if there is some sort of a reactive assimilation process where we can explain a load or a cargo full of trace elements being added, but not at the expense of major elements. And so this is just ongoing work. So stay tuned for the results from this maybe in a few months. So overall, the conclusions from this talk would be that secondary crustal rocks formed along the fractional crystallization path of a mantle-derived primary liquid. We know that at least some of the Apollo secondary crustal samples assimilated substantial amounts of earth creep, but we also know from the fractional crystallization models that the MG suites require very little to no primary crustal assimilation. Then we can say overall that secondary crustal magmatism may have peaked around 4.34 billion years, which also explains the zircon peak at the same time. So that's it. Thank you, and I'm happy to take questions.
Thank you, Ananya. And yeah, we'll go ahead and open it up to questions. So for those that are online, if you want, you can raise your hand or you can put something in the chat. And for those here in person, you guys know the drill. Raise your hand or you can throw something at me. Either way, you can get my attention. So go ahead, Lars.
So Ananya, very interesting. I like all the summation of everything you're trying to put together here. My question is, what do you think about the mineralogy of creep? Because the way the geochemists like myself have used it is kind of like pixie dust, you know, and you basically have something that's dominated by a series of trace elements, you know, like phosphates mostly, maybe a tiny bit of case bar, a little bit of quartz kind of thing, and essentially no iron because that's been removed in the IBC cumulates, which you know have likely been removed physically by sinking or something like that. And so it seems to me that your premise that you can't add much creep in, it really is dictated by what you're assuming the mineralogy of creep is. And I don't know what we have for that, given that it's thought to form after 99.5 to 99.9% crystallization of something. And thermodynamic models, at least in the old days, weren't good enough to go there.
Actually, that's a great question, Lars. And this is something that we've been sort of, I guess, trying really hard to brainstorm. So one thing is there are some experimental studies of lunar magma ocean crystallization, which show that that very end that they went up to is actually very iron enriched. I mean, it's not as titanium enriched because ilmenite may have already crystallized, but the last bit is actually very, very iron enriched. And this recent study that came out by Yixin Zhang et al., they actually show that that very, very iron enriched last bit that you see, that liquid, if you keep crystallizing that, you can actually end up hitting silica liquid immiscibility, which of course, is a different thing by itself. But overall, I think from the current experimental studies that we have, we do think that even after ilmenite crystallization, you can still have a very, very iron-rich liquid left over. Something that would have even like close to 38% FeO in it. And so, if you talk about the mineralogy of that, let's say before hitting silica liquid immiscibility, Well, obviously, you would have to have very iron-rich pyroxenes there. That would probably take in the bulk of that iron. Iron-rich olivine, that's also a possibility, of course. And then you could have very iron-rich spinels crystallizing there. And of course, as you said, like these very last bit of liquids, they would be super enriched in trace elements. So you can also have some trace element-rich phases like phosphates and other things too.
Thanks.
And this is, I think, I'll just add to that. And the fact that, this last bit of liquid could still be so iron rich is actually worrying for us, because the trace elements here tell us that, you can have so much of ore creep assimilation, but then if you really have that iron rich liquid, assimilating, that would have a severe major element penalty to that. So there has to be a way to explain that.
So I raised my hand. It's Justin.
Hey, Justin.
May I ask a question?
I think so.
I'm
Please.
going to ask a question.
Yeah.
I think the room is muted.
Okay. So
I apologize. I was muted. My apologies. Chip was in the midst of asking a question.
oh, sorry. Okay, go ahead,
But
Chip.
Justin, you can go ahead first, and then we'll get to Chip.
Okay, maybe we're asking the same question. I'm just kidding. So I like the approach that you're taking, and I think that this is a outstanding problem for a variety of different types of data. Maybe it's more of a comment than a question, but it leads to more questions, which is much of what you're and Isaiah are modeling, are mixing processes.
Mm-hmm.
And so are we basically just saying that all of this exciting activity is happening in a very, very short time period? Basically everything, the entire record that we have for basically all the rocks in the moon?
By all the rocks in the moon, you mean like the secondary crustal rocks mostly?
Well, all the rocks that you talked about and showed on your diagram.
Yeah, so of course, that diagram that I showed had some really well-dated MG suite rocks, which, lie close to that zircon peak that we see at 4.34. The ferronanorthosites are older, which is, again, good news in terms of, how we understand the petrogenesis of these rocks. And again, like any phase of magmatism, whether it's on the Earth or on any other planet, there's a certain period across which they occur. And the peak could be at a certain time, but that doesn't mean that, you have a switch that you turn on and everything happens, and then, you have a switch you turn off and everything shuts down. But so, I'm thinking about this from the perspective of this LPSC abstract that was presented, where they dated some zircons in MG suite samples, which were actually older than, the 4.34 here. And it's possible that some of these MG suites may have formed earlier than the peak. And then, you have the peak. And then if you get more samples, I think it'll be a better sense of, exactly what that curve looks like if we had a way to plot magmatism versus time. But at least the fact that, with what we have with the high quality geochronology on the samples that are available right now for the MG suite and the QMD class, and the fact that it lines up with the detrital zircon peak is something that cannot be ignored. And we have a petrogenetic process to explain that. I don't know if that answers your question.
Somewhat, yeah. I guess it's a question that's also a loaded question, which is that you can see mixing relationships that make straight lines as well. Clearly, the zircon ages themselves, they're, I think, fairly confident. Well, fairly confident that they are a closed system, but they could be a reset, or could be some short period. But you can have lines that form on isochron diagrams that are due to mixing, and this is a long time ago, and so some you were talking about some ages that are slightly older. When does the resolution of our data allow us to say this is a sort of a single event on the moon that's explaining all this, versus we have rocks and processes that are happening over a sort of 100 million year time period, or 50 million year time period, depending on the resolution that we ascribe to this, various times, right? I mean, is there an MG suite period that's 150
here, Justin?
Of course.
So the questions are not answerable with the samples we have. But let me just, as a chronologist here, let me just explain what we have. First of all, if you look at the old zircon ages, they're only from nanosims. If you look at the 1280 ages on the same spots, they're all younger. In addition, the rock from those old zircons has been dated significantly younger than the zircons themselves. So I don't know who's right in all this, but they certainly should not be taken as gospel. Second thing is regarding the magnesium suite and the ferroanorthosite suite. Let me start with the easier of the two. If you look at the bulk rock Sumerian neodymium that has been done on something like 10 or 15 of these rocks by various groups, they all lie on something like a 4.3 something, 4.34, 4.35 kind of billion year isochron, which suggests that they're all fairly closely related. Of course, at the same time, there's nothing particularly old there. The advantage of this approach, of course, is that slow cooling isn't going to affect things because you're analyzing a bulk rock, and so you're going to get something that should be representative of the system. However, you have the caveat that you're making the assumption that all these rocks are cogenetic and related. But that's probably the best evidence we have that magnesium suite magnetism is short-lived and in a pulse. The QMD class has the same age, and the uncertainty on that by 5 different isochrons is about 500,000 years. So that age is very well defined. The ferroanorthosites are a bit of a mixed bag, and as you and I have talked several times, the anorthosites are really only from Apollo 16. So we may be doing the chronologic equivalent of walking up a dip slope of a volcano and saying everything's the same because we're analyzing the same lava flow over and over and over again. Nevertheless, we've got 4 or 5 ages now. They all agree. If you plot them on that same sort of whole rock isochron, they give you the same age of about 435, something like that. So from my perspective, I think most of the reliable chronology, and I don't consider the zircon chronology reliable for the most part, it seems to suggest that these things are related over a very short period of time. But again, I mean, we don't have much data, and this is a guess.
Okay, thanks.
Thank you for that, Lars, and thank you, Justin, for your question. Okay, now that I'm unmuted, Chip, do you want to go ahead and ask your question again? Apologies for that.
Oh, that's okay. The quartz monzodiorite that Lars provided some chronology from, is in a breccia 15405, and it's associated with rhyolites or felsites and creep basalts. Do you think there's any petrologic relationships among those three rock types within the same breccia?
So the felsites, of course, and you said there's a rhyolite as well. I mean, those could definitely be petrogenetically related to the QMDs, just from the major element perspective, I can say. The Mare basalt, I don't know if that particular Mare basalt has been dated or not.
It's creep basalts.
Oh, it's creep basalt. Okay, sorry.
Creep basalts.
Okay, has that been dated or?
Yeah. As has, I think, as has the felsite too.
Okay.
And they're all relatively, they're much younger supposedly based on, this old set of chronology.
Okay. I cannot say anything about the creep basalts off the top of my head, but definitely if I think of this petrogenetic process that we're talking about here, which is, following the liquid line of descent, then yes, the rhyolites and the felsites can definitely be related to the QMDs.
Thank you, Chip. Do we have any other questions or comments for Ananya? Oh, go ahead, Steve.
Steve Simon here. I have a couple of thoughts on the earth creep, getting back to that.
Mhm.
From observations of Mare basalt metastases, I'd expect the last liquids to be very silica rich. So I'd expect the earth creep to have more pyroxene rather than olivine. And also at such high degrees of prior crystallization, the earth creep would be likely to occur in isolated pockets. And they could evolve differently. I don't expect such late liquids to all be in communication globally. So there could be multiple components or multiple compositions.
Yes, there could be. I agree with you. And also the fact that there could be silica liquid immiscibility as well, which has been demonstrated by a recent study that sort of adds to this possibility of like more lithologies that could be explained from earth creep.
Thank you, Steve. Any final question or thoughts? Okay, well, I want to thank you, Ananya, once again.
Thank you so much for the opportunity as well as for asking these excellent questions. Thank you.
No, it was a pleasure having you. And then for everyone, again, this was our final of the semester, our final planetary sample seminar series. So we wish everyone a wonderful rest of the semester. I know we're coming up on finals and all that kind of stuff. So good luck with everybody, and then enjoy your summer. And we hope to see you guys back in the fall.
Back in the fall.
Yeah.